All right, howdy. Can you guys hear me? Okay. So, the plan for today is I'm going to again go through questions for maybe the first hour or two. And then I'm going to kind of shift towards something more directed. And I hope to kind of end by live solving a lot of homework 7. So I guess we'll start with the questions part of this. So Kyle asks, can we do problem 3B from exam 1? So let me find exam 1. Actually, how about this? I just do this. Scroll down through here. Keep going back. Here's exam 1. So let me open this. Okay, so the first request was to compute problem 3, part B from exam 1. So let me take this, go over here, and bring this to PowerPoint. Okay, so what we want to do is we want to compute the determinant of the matrix A using row reduction. So the first thing we're going to do here is we're going to set row 2 to be equal to row 2 minus 3 times row 1. We're going to set row 4 to be equal to row 4 minus 4 times row 1. Or actually, I'm sorry, 3. That should be row 3. And then we're going to set row 4 to be equal to 1. Actually, row 4 minus 1 times row 1. So with this first batch of row operations, what we're trying to do is we're trying to kill off this term, and this term. And so if we carry them out, let's see what we get. We know that the first row stays the same, so we have 1, 2, 3, 1. For the second row, we're going to have 0 here, 1 here, and 0 here. And then here we're going to have, let's see, so if I take 2 times 3 and I subtract it from 2, actually, sorry, 3 times 3 and I subtract it from 2, I should have -7 here. Now down here, I'm going to have, let's see, 0 and a 0, and so I'm subtracting 4 times 2 from 6, so I'm going to have -2 here. And I'm subtracting 4 times 3 from 5, so I'm going to have -7 here, I think. So if you guys catch me making any arithmetic errors as I go, let me know. How about I do this? So down here, I'm going to have 0, 0, 1, and what else? 4. So I only have to figure out this last entry. So I'm subtracting 4 times 1 from -1, so this should be -5. So this completes the first batch of row operations. What we want to do is we want to make this matrix upper triangular using just type 3 row operations. So I'm going to say that right here. To easily compute det A, make it upper triangular using only type 3 row operations. So I guess I should say you don't have to use only type 3 row operations. But the reason we want to do this is because if we don't use type 3 row operations, then we have to start keeping track of signs, we have to start keeping track of various factors that we incorporate into our elementary matrices that we're using. So to make things as simple as possible, you only use type 3 row operations, since type 3 row operations preserve the determinant. So what I'm going to do here to simplify things a little bit is I'm going to set row 3 to be equal to row 3 plus 2 times row 2. And you can see that will get rid of the -2 here. So we're left with 1, 2, 3, 1, 0, 1, -7, 0. Here, this is the bottom row is going to stay the same, so I'm going to have 0, 0, 1, 4. This is going to stay -5. This is going to stay 0. This is going to go to 0. And I'm adding 2 -7 to -7, so I'm going to have -21 here. Okay. So next thing I'm going to do is I'm going to set row 3 to be equal to row 3 plus 21 times row 4. And this will get rid of this -21. So if I do this, let's see what I get. Well, I'm going to have 1, 2, 3, 1, 0, 1, -7, 0. And 0, 0, 0. And then -5 plus 21 times 4, which is the same thing as -5 plus 84, which is equal to 79. So I'm going to have 79 here. And then I have a 1 and a 4 here. So now I am almost done. So let's take this to another page. This is not upper triangular, but it almost is. And the way to make it upper triangular is to do a row swap. Now I was trying to avoid doing row swaps because row swaps introduce a sign of -1. But after doing a row swap, particularly swapping row 3 with row 4, I get the following matrix. 1, 2, 3, 1, 0, 1, negative 7, 0, and then 0, 0, 1, 4, and then 0, 0, 0, 79. And the determinant of this just ends up being equal to 79, which means the determinant of the original matrix well, let's look at it. We had to do one row swap along the way, which changes the sign by -1, but everything else we did was type 3 row operations, which preserve the determinant. So it follows that the determinant of the original matrix is negative 79. So that completes the computation of the determinant of this matrix using row reduction. So that finishes the question 3B from exam 1. Ryan Chong asks, will second order differential equations be on the exam? By second order differential equations, I assume you mean things like y double prime is equal to 5y. And the answer is no. Second order ODEs will not be tested. Only systems. Only systems of first order equations. Okay, so let's move on. Ultimate Calculator asks how many questions are on the final. So I haven't actually finalized it yet, though I have a draft written. It'll either be between 10 to 12 questions. I will also say that it is more computational than proof-based in comparison to exam 2. I think I've already said that in the Discord, though. So let's see what else. And I'm not going to give specific answers to what the ratio of questions from exam 1 and exam 2 are. I will say that the majority of questions, though, do come from chapters 5 and 6. But they tend to use ideas that were present in the earlier chapters as well. Hannah Green asks, can we do a Gram-Schmidt example? And yes, we can. So let's do a Gram-Schmidt example. So I'm going to do a QR decomposition problem. And I'm going to consider the matrix A equals, say, 1, 1, 0, 0, 3, 1, and then 1, 2, 1. And then here's the problem. Find the QR decomp of A. So let's label these columns. This will be V1, this will be V2, this will be V3. So the first thing we're going to do is we're going to run through our Gram-Schmidt process, which tells us that U1 is going to be equal to V1 divided by the norm of V1. And if we go over here, we can compute the norm of V1 to be equal to the square root of 1 squared plus 1 squared plus 0 squared, which of course is just the square root of 2. So this is going to be equal to 1 over the square root of 2 times the vector 1, 1, 0. And now, according to Gram-Schmidt, U2 is going to be equal to V2 minus the scalar or the vector projection of V2 onto U1, so this quantity, divided by its magnitude, or its norm. So the first thing we have to do is we have to compute what this vector is, then we have to compute its length. So let's do the calculation of the inner product of V2 with U1. This is going to be equal to 1 over the square root of 2, and then multiplied by, let's see, 0, 3, 1, taking the inner product of this with this vector, so 1 times 0 plus 1 times 3, and then plus 0 times 1, so it just ends up being equal to 3 over the square root of 2. So V2 minus 3 over the square root of 2 multiplied by the vector 1, 1, 0 is going to be, let's see, so if I subtract, actually I'm sorry, square root of 2 here, and this is also divided by the square root of 2, so this should actually just be divided by 2. So let's see what this is. I'm going to get negative 3 over 2 here. And then I'm going to get out of steam. For my second entry, I have to look at 3 minus 3 over 2 times 1. So 3 minus 3 over 2, which is just positive 3 over 2. And then down here, I'm just going to get 1. So this right here gives me V2 minus the inner product of V2 with U1 times the vector U1. So now I have to compute its magnitude. So the magnitude of V2 minus the inner product of V2 with U1 times U1 is going to be, let's see, the square root of 9 over 4 plus 9 over 4 plus 4 over 4, all of which simplifies to the square root of 22 over 2. Actually, can I do this slightly better? No, I can't. So square root of 22 over 2. Okay, thus we see that U2 here is equal to the vector -3 divided by the square root of 22, 3 divided by the square root of 22, and 2 divided by the square root of 22. So let me sanity check myself real quick to make sure this works. Yeah, if I take the inner product of this with this, I get 0, which is right. This is definitely a unit vector, so far my computations are correct. So let's take it all to a new slide. So now I have to find U3. U3 here is going to be equal to V3 minus the inner product of V3 with U1 times U1 minus the inner product of V3 with U2 times U2. And then I have to divide all of this by its norm. So I'll just put ... here for the thing right up here. So let's go back over here and grab our matrix. And let's see the calculations we have to do. So first things first, let's consider the inner product of U1 with V3. So this is going to be, let's see, 1 over the square root of 2, and then times 1, or actually times 1 times 1, plus 1 times 2, plus 1 times 0. So in fact, I just get 1 times 1, plus 1 times 2, and then the other thing cancels because it's just 0, so I get 3 divided by the square root of 2. So now I know what V3, the inner product of V3 with U1 is. I also have to compute the inner product of V3 with U2. So again, I'm going to have like a 1 over square root of 22 on the outside. And then, what else am I going to have? So 1 times -3. So -3 times 1 plus 3 times 2 plus 2 times 1. And so this simplifies to 1 over the square root of 22 multiplied by 5, I believe, because this is 8 minus 3, so yeah. I'll just put a 5 in here. Okay, so V3 minus the inner product of V3 with U1 times U1 minus the inner product of V3 with U2 times U2 is equal to 1, 2, 1 for the V3, and then minus 3, or sorry, it should be a minus sign, inequality, minus 3 over 2 times 1, 1, 0, and then minus 5 over 22 times the vector negative 3, 3, and 2. And so now we have to do a bit of calculating to fill in this vector. So at this point, I'm going to resort to using Wolfram alpha. So for my first component, it's 1 minus 3 over 2, and then minus 5 over 22 times negative 3. And so we just get 2 over 11 for our first component. For our second component, we have 2 minus 3 over 2, and then minus 5 over 22 times 3. So we get negative 2 over 11. And then finally, we're going to have 1, and there's not going to be a second term here, so it's just going to be minus this times 2, which gives us 6 over 11. All right, now I can try to sanity check myself real quick to make sure everything is working. One way to sanity check myself is to take the inner product of this with this vector and make sure I'm getting 0. I can see that I get 0 really quickly. I can also see that if I take the inner product of this with this vector, I'm getting 0. So right now, this computation has given me a vector that is orthogonal to u1 and u2. So it remains to compute its length. And that's pretty easy. The norm of the vector, 2 over 11, negative 2 over 11, and 6 over 11, is going to be equal to the square root of 4 plus 4 plus 36, all divided by 11. So this will be the square root, or rather 2 times the square root of 11 divided by 11. So u3 is going to be equal to the vector 2 over 11, negative 2 over 11, 6 over 11, times the reciprocal of this, its norm. So 11 divided by 2 over the square root of 11. And so this is going to give me the vector 2, negative 2, 6, all multiplied through by the scalar 1 over 2 times the square root of 11. And so now I have u1, u2, and u3. So let's write them all down. So u1 was the first thing we calculated. It was 1 over the square root of 2 times the vector 1, 1, 0. u2 was the vector negative 3 over the square root of 22, 3 over the square root of 22, 2 over the square root of 22. And then finally, we just figured out what u3 is. And so we have applied Gram-Schmidt to our matrix. or rather the column vectors of our matrix, to find three vectors u1, u2, and u3. And all that remains is to interpret them as giving a QR decomposition of A. So let me go through the interpretation. The interpretation is rooted in the following fact. V1 is equal to the magnitude of V1 times U1. V2 is equal to the magnitude of V2 minus the inner product of V2 with U1 times U1, all multiplied by U2, and then plus the inner product of V2 with U1 times U1, and then V3 is equal to the inner product of V3 minus the inner product of V3 with U1 times U1 minus the inner product of V3 with U2 times U2, all multiplied by U3 plus the inner product of V3 with U1 times U1 plus the inner product of V3 with U2 times U2. Okay, so QR is going to be equal to the product of two matrices, a Q and an R matrix. And let's write down what our Q matrix is because we already have that in hand. So here we're going to have 1 over the square root of 2. Here we're going to have 1 over the square root of 2. Here we're going to have 0. Here we're going to have negative 3 over the square root of 22. Here we'll have positive 3 over the square root of 22. And here we'll have 2 over the square root of 22. And then for our final thing, we have 1 over the square root of 11. And then we have negative 1 over the square root of 11. And then we have 3. Is that positive? Yeah, positive 3 over the square root of 11. And this is our matrix Q. And we also have this matrix right here, which is R, and its entries are R11, R12, R13, R22, R23, and R33. And we know that R is upper triangular, so all its other entries are going to be 0. And the question is, what are these R's? And it becomes a matter of interpreting them, because we know that this matrix right here is equal to the matrix V1, V2, V3. And the relations between the R's, the Q's, or the vectors U's, and the vectors V's is precisely given by these relations up here. So R11 is just going to be this quantity. And then this quantity right here is going to be R12. This quantity right here is going to be R22. This quantity right here is going to be R33. this quantity right here is going to be R13, and this quantity right here is going to be R23. And this is necessitated precisely by the form of this matrix equation. When we multiply the first vector here by this matrix, we should be getting V1. When we multiply the second vector here by this matrix, we should be getting V2. When we multiply the third vector by this matrix, we should be getting V3. And so that's precisely what these quantities have to be. And now we can go back through our computation to figure them all out. So let's write down our R matrix. Let's start by figuring out what R11 is. Well, that's going to be the magnitude of V1. And we computed the magnitude of V1 to be the square root of 2. We can compute R12 here, or rather we can find our computation of R12. That is precisely the inner product of V2 with U1, which we found to be 3 over the square root of 2. And then we can try to find R22, which is this magnitude. We computed this magnitude right here, and we got the square root of 22 over 2. Of course, we have 0 here, 0 here, 0 here. And then we can look at what R13 is. Well, we computed R13 right here, and we got 3 over the square root of 22. Or wait, was that 3 over the square root of 2? And then we can look at R23 here, which we know to be the inner product of V3 with U2. And we know that to be 5 over the square root of 22. And finally, what we need to know is we need to know what R33 is, but it's precisely going to be the magnitude of this vector, which we computed on this slide. Actually, no, it was the next one. We computed that the magnitude of this vector right here was 2 times the square root of 11 over 11. And this gives us our R matrix. So now we have our R matrix, and we also have our Q matrix. And so this right here together gives us the QR decomposition of A. So these are long, painful computations, but they all basically hinge on the following formula, which is that UI is always going to be equal to VI minus the sum from I, or I should say from j equals 1 to I minus 1 of the inner product of VI with uj times the vector uj divided by the norm of this. And the calculation is recursive. So if you know all the ui's up to ui minus 1, you can use this formula to figure out what ui itself is. And you just run through these computations until you've computed all the u's. And then along the way, you've already computed everything that you need to put in your R matrix to find the QRD comp. Okay, so that goes through a Gram-Schmidt example. Brian Chong asks, can we do number 5 on exam 2? Let me see. So has file Where is exam 2? Here it is. All right. So I did post a write-up of this question, but I'll solve it for you guys to kind of walk through the process of what you have to do. All right. And as I corrected during the exam, this is less than. So let's see. How do we approach this? Well, a basis for P4 is x cubed, x squared, x and 1. And so let's call this basis E. And let R1 have the standard basis. Then L has a matrix representation. R4, so these are coordinate vectors with respect to this basis, E, into R1 standard. And the matrix representation here is given by a matrix B. So let's figure out what B is. So if this thing right here is our basis vector F1, and this is our basis vector F2, and this is our basis vector F3, and this is our basis vector F4, then we know that F1 maps to 1 raised to the third plus negative 1 raised to the third, which is equal to 0. We know that F2 maps to 1 squared plus negative 1 squared, which is equal to 2. We know that F3 maps to 1 plus negative 1, which is equal to 0. And we know that F4 maps to 1 plus 1, which is equal to 2. So we can write down the matrix representation with respect to coordinate vectors in E and the standard basis vector of R1. And B is given by the following matrix. So it's going to be a 1 by 4 matrix. So the first entry here is 0. The second entry here is 2. The third entry here is 0. And the final entry is 2. So what we want to ask is what is a basis for the null space of B? Well, here's what we know. So if B is equal to this, then this right here is the first non-zero term in the row. So this is a bound variable. And this right here, this right here, and this right here are all free variables. So what we have is 0 times x1 plus 2 times hold on one second. Plus 2 times x2 plus 0 times x3 plus 2 times x4 is equal to 0. And this in turn tells you that x2 is equal to negative x4. So the null space of B is equal to the set of vectors x1 and then negative x4 and then x3 and then x4, where x1, x2, x1, x3, and x4 are all real numbers. So this is equal to the span of, actually let me write it on another slide. This is equal to the span of the vector f1, f3, and f2 minus f4. Actually, maybe I'll just switch the negative sign to be consistent. So recall that f1 corresponds to x cubed, f3 corresponds to x, and f2 or minus f2 plus f4 corresponds to negative 1 plus x squared. So the kernel of L may be regarded as the span of x cubed, x, and -1 plus x squared. So that is kind of the most rigorous way to compute the kernel. Okay, so we've done 5 on exam 2. Max Rod asks, will there be theory proof questions on the final? So yes, there will be at least 1 or 2 theory proof questions on the final. I can even kind of tell you what they'll be related to. Probably one of them will be related to least squares. And that's my hint for tonight. Connor asks, are there any questions we should memorize for the exam? So, or any equations we should memorize for the exam? Yeah. So, quite a few, I would say at minimum. Let me see what else. Okay, so let's see, what's the next question? Let me look at Benjamin's question. So let me pull up that homework. So let me kind of explain what I'm typing about here. Suppose we have a matrix like 1, 1, 0, -1, 1, 0, and then 2, 0, 0. So call this matrix A. Then we can denote the column vectors here by v1, v2, and v3. And here's a key fact. The set v1, v2, v3 does not form a basis for the column space of A. So we can't apply the Gram-Schmidt algorithm. Instead, we need to choose a subset of columns that do form a basis for the column space of A. And apply Gram-Schmidt to this subset. So this only happens when the columns themselves don't form a basis, but it's general behavior. In the example given in problem 8, in fact, for both of these examples, these two, the columns do form a basis, so you don't have to worry about it. But I just want to indicate what happens in general. Okay, so that handles Benjamin's question. Savannah asks, can we do number 7 on exam 2? So let's go over here and take number 7. This is actually not that hard of a problem. If you know what's going on, it doesn't actually involve that much computation, so. All right, first thing we're going to do here is we're going to compute the null space of A. And we can compute this via row reduction. So let's go through it. We start with our matrix 1, 1, 3, 0, 2, 3, 7, 1, 3, 4, 11, 0. First thing we're going to try to do is we're going to try to get rid of this 2 and this 3 because we want to put it in row reduced echelon form. So what we do is we set row 2 here to be equal to row 2 minus 2 times row 1. And we set row 3 here to be equal to row 3 minus 3 times row 1. And so let's see what we get. We get first row stays the same, so 1, 1, 3, 0. Second row becomes 0, 1, 1, 1. Third row becomes 0, 1, and then 2. And then this stays 0. Let me sanity check myself on this real quick. Yeah, this looks right. So next thing I do is I set row 3 equal to row 3 minus row 1, or minus row 2. In which case the first row stays the same, so 3, 1, 1, 3, 0. The second row stays the same, so 0, 1, 1. My third row now becomes 0, 0, 1, and then negative 1. All right, so this is looking good. Next thing I do is I set row 1 to be equal to row 2, or sorry, equal to row 1 minus row 2. What I'm trying to do is get rid of this 1 so that this leading 1 is the only one in the row. So, this is the same thing we do when we're putting a matrix in row reduced echelon form. If I do this, then I get, well, the bottom 2 rows stay the same. So 1, 1, 1, 0, 1, or sorry, 0, 0, 1, negative 1. First row becomes 1, 0, 2, negative 1. And then finally, the last thing I'm going to do is I'm going to set row 1 equal to row 3, or sorry, equal to row 1 minus 2 times row 3, because I'm trying to clear out this 2. And I'm also going to set row 2 equal to row 2 minus row 1. The reason I'm doing that is I want to clear out this 1. So my bottom row is going to stay the same. I'm going to have 0, 1, 1, 0, 0, 0, 1, negative 1. The second row is going to become 0, 1, 0. And then I believe I get 2 here. Let me check myself. Yeah, that's right. And then up here, I'm going to get 1, 0, and then 0. And then I'm subtracting 2 from -2. So I believe I get +1 here. Let me check myself, make sure I did this right. Because I know I did it right when I solved it yesterday. So yeah, I did it right. Okay, so that's good. So this right here is the row reduced echelon form of A. So here's what we can observe. Observe that the rank of A, which is equal to the dimension of the column space, has to be equal to 3 because the first 3 vectors are linearly independent and the last vector can be expressed in terms of them. So the rank of A is equal to 3. By since the rank of A is equal to the rank of A transpose, and the fact that the rank of A transpose plus the null space of A transpose is equal to, or I'm sorry, the rank of A transpose plus the dimension of the null space of A transpose is equal to 3, it follows that, well, recall that this is equal to 3. It follows that the dimension of the null space of A transpose is equal to 0, which implies that the null space of A transpose is equal to 0, the 0 vector space. It also implies, since rank of A transpose is equal to 3, the columns of A transpose form a basis for R A transpose. So R, or this is the column space of A transpose, is equal to the span of the column vectors of A transpose, which are precisely 1, 1, 3, 0, um, 2, 3, 7, 1, and 3, 4, 11, 0. So we have leveraged a lot from just one computation. We were able to compute the row-reduced echelon form of A. By computing the row-reduced echelon form of A, we observed that the rank of A was 3. And that told us that the rank of A transpose was also 3. The fact that the rank of A transpose was 3 taught us by the rank nullity theorem that the dimension of the null space of A transpose had to be 0, which consequently means that the null space of A transpose is just the 0 vector space. And it also told us that the 3 columns of A transpose have to form a basis. So we've actually determined a lot, but we've also determined that since the standard basis appears in the first 3 columns of the row-reduced echelon form of A, we have that the column space of the matrix A is simply equal to the span of the 3 basis vectors, which is just R3 itself. So now we know what R of A is. We know what R of A transpose is. We know what the null space of A transpose is, and so all that remains is to figure out what the null space of A is. So here's our fact. The null space of A is equal to the null space of its row-reduced echelon form. So 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, negative 1. And let's remark that this, and this all correspond to bound variables. This corresponds to a free variable. And so from this, we're able to extract that x1 is going to be equal to negative x4. x2 is going to be equal to negative 2x4. And x3 is going to be equal to x4. So this is going to be equal to the span of the vector negative 1, negative 2, 1, 1. So now I have found all 4 of the spaces that the problem asked me to determine, and I was able to leverage it all from a single computation. And now the last thing I have to do is I have to state the relationship between these spaces. Well, here are the relationships. The null space of A is orthogonal to the row space of A transpose. And the null space of A transpose is orthogonal, or I'm sorry, this is column space, is orthogonal to the column space of A, which is the same thing as saying that R4 may be understood as the direct sum of the null space of A with the column space of A transpose, and R3 may be understood as the direct sum of the null space of A transpose with the column space of A. And so these are the orthogonality relationships. All right, so that completes the computation and proof for problem 7. All right, so that answers Savannah's question. The next question is from Brian Chong, which asks if I can do an eigenvalue differential equations problem, and I can do that. So an eigenvalue differential equation. So I'm going to consider the following one. I'm going to set y to be the vector with entries that are functions, y1 of t and y2 of t. And I'm going to maybe try to do something like the matrix A is equal to 1, negative 1, 1, 1. And I'm going to consider the equation y prime is equal to A times y. So, to solve this, find eigenvectors of A. So say v1 and v2 with eigenvalues lambda 1 and lambda 2. Then h1 of t equal to c1 times e to the lambda 1 times t times the vector v1, and h of 2 of t equal to c2 times e to the lambda 2 times t times the vector v2 are both solutions to the system. And if the lambda I are complex, the real part of h1 of t and the imaginary part of h1 of t also form solutions. So you basically have to treat the problem slightly differently depending on whether the eigenvalues are complex numbers or not. If they're not complex numbers, this gives you the solution. And if they are complex numbers, you have to extract the real and imaginary parts of the vector. And each of these two parts will themselves form solutions. So this right here is our strategy. So let's execute it. First thing we need to do is we need to write down the characteristic polynomial of A. So this is P of A lambda, and it's going to be equal to the determinant of 1 minus lambda, negative 1, 1, 1 minus lambda. And this is going to be 1 minus lambda squared plus 1. So this just ends up being equal to lambda squared minus 2 lambda plus 2. And the roots of PA lambda, the characteristic polynomial, are given by the following equation, which is the quadratic formula. 2 plus minus the square root of so negative 2 squared minus 4 times 2, all divided by 2. And so this is the same thing as 1 plus minus the imaginary number. So do I agree with that? Let me think for a second. Yeah, I do. Okay, so I have found the roots of PA lambda, which means now I have to find the eigenvector. V1 associated with 1 plus I. So I want to look at the null space of the matrix. Well, it's the null space of the matrix A minus 1 plus I times the 2 by 2 identity matrix, which is going to be equal to, so here I'll have an I, actually a negative I. Here I'll have a negative I. Here I'll have a negative 1. Here I'll have a positive 1. And this null space is easily equal to be seen using the little trick of basically taking the row here and flipping the components and making one of them negative, is seen to be the span of the vector 1, negative I. So let me just double check myself to make sure. Does this work? Yeah, this works. So what we can do is we can take V1 to be the vector 1 and negative I. And I guess to kind of clarify my terminology, there's a whole vector space of eigenvectors associated with this eigenvalue. But really, I only need to take one of them, and you can take any one in the span. For simplicity's sake, I'm going to take this one. So now I can write down H1. So H1 of t is going to be equal to C1 times e to the 1 plus I times t times the vector 1, negative I, which is the same thing as C1. And now I'm going to use Euler's formula, which tells me that this is the same thing as e to the t times cosine of t plus I times sine of t. And then this is getting multiplied through by the vector 1, negative I, which is going to be, let's see, C1 times e to the t. And then I'm going to have two different vectors here. One vector is going to be multiplied by the imaginary number, and the other vector will not be. So if I multiply cosine t by 1, I get something real, so I'll have a cosine t here. If I multiply cosine t times negative I, I'm getting something that's negative imaginary, so I should have negative cosine t here. If I multiply I sine of t by 1, I'm getting something imaginary, so I should have sine of t here. And if I multiply I sine of t by negative I sine of t, then I'm actually going to get something real, because an imaginary number times an imaginary number, or I times I, is actually just equal to negative 1. So I get positive sine of t here. Okay. Kyle Seaman asks, how did I get those n parentheses values? What are you referring to here? Okay, so going back to the problem here, what I've done is I have written down, so okay, let me go through this again. First thing I did is I wrote down the characteristic polynomial of my matrix, and I solved it, and I found that the roots of it were 1 plus minus the imaginary number. And let me explain how I got this null space matrix. Well, what I did is I took 1 plus I and I plugged it into the matrix 1 minus lambda. Actually, let me maybe do it on another slide to make it very clear. A minus lambda I2 is equal to 1 minus lambda, negative 1, 1, 1 minus lambda. And so then what I'm doing is I'm setting A minus 1 plus I times I2. And this is the same thing as 1 minus 1 plus I minus 1, positive 1, and then 1 minus 1 plus I. And then this is going to be the same thing as negative I, negative 1, 1, and negative I. So is it clear what I'm doing, Kyle? Okay. So that's how we get that we're looking at the matrix A minus the eigenvalue times the identity matrix. We can try to compute its null space. And here I'm using the trick that the null space of a matrix of the form AB, K, A, K, B is always going to be equal to the span of the vector negative B, A. So this is how I'm very quickly figuring out what the null space is the span of. I'm just using this trick. And this gave me the eigenvector V1, where the first component is 1, the second component is negative I. And then I took the eigenvalue, so this is the eigenvalue, and I took the eigenvector, or the associated eigenvector, and I wrote down this function. And now what I'm doing is I'm splitting this function into the real and complex parts. So this right here is really the same thing. Here, I'll take it to another slide to be as clear as possible about it. This is really equal to the same thing as C1 ET times cosine of t sine of t plus the imaginary number, and I'm going to put everything after it in brackets, C1 E of t times sine of t up here and negative cosine of t down here. So this right here is the real part. This right here is the imaginary part. So what I'm going to do is I'm going to define, call it S1. This is going to be my first solution. S1 of t is going to be defined to be C1 ET cosine of t sine of t. And then I also have to define S2 of t. And S2 of t is going to come from the imaginary part, but I have to make one change. So you see here how the index of this constant is 1. I'm going to change that index to 2. So I'm going to make it C2 times E of t. And I'm going to keep everything else. So I'll have sine of t and negative cosine of t. Okay, so let me finish with this example, and then I'm going to kind of go on an elaboration of the question Brian Chong just asked, which is how do we solve for a null space not involving a matrix in the form of the one that I just applied the trick to. So let me finish with the problem that I'm solving, because I'm basically done with it. the general solution, yeah, Benjamin, I will do that right after I finish talking about null spaces. So the general solution to y prime equals a times y is c1 e to the t times cosine of t sine of t plus c2 times e of t times sine of t negative cosine of t. So this completes the problem of solving an eigenvalue differential equation. So now let me answer the other question, which is how do we find the null space of a matrix? So how about I look at a matrix like A equals the matrix 1, 2, and then 1, 3, and maybe this will be 0, 4, and this will be 5, 1. So what I'm going to do is I'm going to note that if B is the row-reduced echelon form of A, then, oh, okay. Well, I'll just change this up slightly. I'm just going to put an imaginary number here, and I'll put a 1 here and an I here. So if B is the row-reduced echelon form of A, then in fact we always know that the null space of A is equal to the null space of B. So the first thing we're going to do is we're going to try to put this matrix in row-reduced echelon form. So what we do is we set row 2 to be equal to row 2 minus row 1. In which case we're going to get 1, 2i, 0, 4, and then 0, I, 1, and then I minus 4. So this and this correspond to bound variables. And this correspond to free variables. So we can express our bound variables in terms of our free variables. Oh wait, I'm sorry, I'm being an idiot. This is not row-reduced echelon form just yet. I have to do one more operation. So the other operation I'm going to do is I'm going to set row 1 to be equal to row 1 minus 2 row 2, because I have to cancel this, and then I get 1 0 negative 2, and then I get 4 minus 2 times I plus 4, or I minus 4. So that is the same as 12 minus 2i. And then the bottom row is now 0, I, 1, I minus 4. So this is not row-reduced echelon form either, but it almost is. And the reason it's not row-reduced echelon form is that you have to recall that for row-reduced echelon form, these leading terms, like the first thing appearing in the first row, or the first thing appearing in each row always has to be 1, which is true for the first row but not true for the second row. So in fact we have to do one more operation. And in this operation what I'm going to do is I'm going to set row 2 to be equal to negative I times row 2. If I do this, I get the matrix 1, 0, negative 2, 12 minus 2i, and 0, 1, negative I, and then positive 4i plus 1, I believe, if I've done that correctly. And that will give me the actual row reduced echelon form of A. Okay, so now that I've done this, and let me actually tell you guys something that's kind of important. So I just, this is kind of a general fact, but I haven't really focused too much on teaching complex numbers, but the fact is that 1 over a plus bi is actually always going to be equal to a minus bi divided by a squared plus bi, or plus b squared. So you'll notice that here, what I essentially wanted to do was I wanted to get rid of this I, which meant I was dividing this entire row by I. But then 1 over I is the same thing as negative I divided by 1, according to this formula. That's why I multiplied the second row here by negative I. Anyways, now I have the row-reduced echelon form of the matrix. So this tells me that x1 is going to be equal to 2 times x3, and then plus 2i minus 12 times x4. And it also tells me that x2 is going to be equal to I times x3 plus negative 4i minus 1 times x4. Recalling that this and this correspond to free variables, and this correspond to bound variables. And so I'm able to solve basically the system, if this is the matrix B, I'm able to solve the system B of x equals 0. Sorry, I'm being an idiot. My mind starts to fry after about 2 hours. These are the bound variables. These are the free variables. And I'm able to express the bound variables in terms of the free variables to solve the equation bx equals 0. And I get these equations, which tells us that the null space of B is equal to the set of vectors 2x3 plus 2i minus 12 times x4, ix3 plus negative 4i minus 1 times x4, and then x3, x4, where x3, x4 are real numbers. But I also mentioned we can extract from this a basis, and that's pretty easy. So let me show you guys how that's done. So this is the same thing as the span of the following two vectors. First, I'm going to look at x3, and I'm going to find the vector that I get when I set x3 equal to 1 and x4 equal to 0. Well, if I do that, then I'm going to get 2 here, I here, 1 here, and 0 here. And then I'm going to look at the vector I get when I set x3 equal to 0 and x4 equal to 1. And that's going to give me 2i minus 12 for my first component here, negative 4i minus 1 for my second component, 0 for my third, and 1 for my fourth. And so these two vectors that I've just written down form a basis for the null space of B, and hence also form a basis for the null space of A. Kyle asked, will something like this be on the exam? Okay, so I hope this answers Brian's question. In a way, the problem of computing the null space of a matrix with complex numbers involved is not really any different from the process of computing the null space of an ordinary real matrix. The only difference is that you sometimes have to multiply and divide through by complex numbers, in which case you have to use this formula. But then other than that, everything else is basically the same. So the other thing people were curious about was least squares types problems. So Marcus asked about them, as did Benjamin. So let's do a least squares type problem. So let A be equal to, say, 1, 2, 3, 0, 1, 1, 1. And let's let B be the vector, 1, 0, 1, 0. And so here is the problem as stated. Find the least squares solution of AX equals B. And this basically means minimize the distance of AX to B. So here's how we do this. We note that we have the following formula. X will be equal to A transpose times A, you take the inverse of it, and then you multiply it through by A transpose times B. And this is the solution. Assuming A has linearly independent columns. In fact, this is not just the solution, this is the unique solution under the assumption that A has linearly independent columns. If you want, you can go back through my lecture and you can see a derivation of this formula. But now we're going to put this formula into action. So the first thing we're going to have to compute is we're going to have to compute A transpose times A. It's going to be the same thing as 1, 2, 3, 0, 1, 1, 1, multiplied through by 1, 2, 3, 0, 1, 1, 1, 1. And if I do this calculation, I'm going to get a 2 by 2 matrix. If I multiply this column by this row, I get 4. If I multiply this column by this row, I get 6. If I multiply this column by this row, I get 6. If I multiply this column by this row, I get 1 plus 4 plus 9, so I get 14. Now, the determinant of A transpose times A is going to be 4 times 14 minus 36. So what is 4 times 14? So that's same as 7 times 8, which is 56. So this is 56 minus 36, which is equal to 20. So A transpose A inverse is equal to 1 over 20 times the matrix. 4, 14, negative 6, negative 6. Let me sanity check myself on this really quickly. Yeah, this looks right. So now I know what A transpose A inverse is, which helps me a lot towards applying my formula. The other thing I need to figure out is I need to figure out what A transpose B is. So let me go to another slide and do that. Well, A transpose is 1, 2, 3, 0, 1, 1, 1, 1. And then I multiply it by my vector 1, 0, 1, 0. And this is going to be, let's see, I'm going to get 4 for my first component and 2 for my second component. So now I have everything I need because I know that X is equal to A transpose A inverse multiplied through by A transpose B. So this tells us that X is equal to 1 over 20 times 4, 14, negative 6, negative 6, multiplied through by the vector 4, 2. So this is going to be 1 over 20. And then, let's see, My first entry is going to be 4 times 4, which is 16, minus 12. So I get 4 here. My second entry is going to be 4 times negative 6, which is, of course, negative 24 plus 28. So I get 4 here. So this gives me 1 over 5 times the vector 1, 1. Okay, so Marcus asks a question. For one of my examples in my lecture, I took the least squares answer and multiplied it by the original matrix. And he asks, when and why do we do this? Well, here's the question. Let R of A, or how about this? Let S equal R of A. Find the distance from the vector B to the space S. So this is a different problem than the one I just stated, but I'm going to let A be the same matrix. So A is this matrix, and B is this vector. And I haven't asked you to find the least square solution. Instead, I've asked you to find the distance from the vector B to the space S. So how do I go about this? Well, step 1, find the least square solution. X hat to AX equals B. We've already done that. And we found that X hat here is equal to 1/5 times the vector 1, 1. And then step 2, because this is the thing that minimizes the distance from AX to B, the distance from B to S is the magnitude of AX hat minus B. So this problem that I've just stated has 2 steps. Step 1 is to find the least square solution, which we just accomplished, and step 2 is to actually find the distance from the vector B to the subspace spanned by the columns of A, the column space. And the answer is that the distance from B to S is given by the magnitude of this vector. So let's figure out what that is. So A times X hat is going to be the same thing as 1/5 times 1, 2, 3, 0, 1, 1, 1, 1, multiplied through by the vector 1, 1, which is going to give, or sorry, there should be a 1 down here, which is going to give me 1/5 times 2 here, 3 here, 4 here, and 1 here. So now AX hat minus B is going to be the vector 1/5, and then 2, 3, 4, 1, and then minus the vector B, which we call as this. So we're going to write it as minus 1/5, 5, 0, 5, 0. And so this is the same thing as 1/5 times 2 minus 5, so I get negative 3 here. 3 minus 0, so I get positive 3 here. 4 minus 5, so I get negative 1 here. And then 1 minus 0, so I get 1 here. And that is the vector ax hat minus b. And so now the final thing I have to do is I have to compute the norm of 1/5 times the vector I just found. Negative 3, positive 3. Negative 1, positive 1. And this is going to end up being equal to 1/5 times the square root of 3 squared plus 3 squared plus 1 squared plus 1 squared, which is going to be 1/5 times the square root of 20. And so this will be the same thing as 4 times the square root of 5 divided by 5. And this right here is the distance from B to S. All right, so that handles this question. Benjamin also asked if I could go over the theory behind least squares. So I'm going to do that really quickly. The theory behind least squares. So here's how it goes. Consider ax equals b. The equation might not be solvable. The equation might not be solvable, which is fine. So, we wish to find x minimizing the norm of ax minus b. Basically, if we can't make a of x equal to b, we want to get a of x as close to possible to b. So how do we do this? Well, there's two approaches. One that's based on calculus and one that's based on linear algebra. If you want to understand the calculus proof, you can open any course on statistics or machine learning, and they'll have that within the first 5 pages of the book. Instead, I'm going to do a linear algebra-based proof that is, what I did in lecture. And the linear algebra-based proof is based on the following idea, which is if A is an M by N matrix, then our M may be expressed as the column space of A direct sum with the null space of A transpose. And we also know that the null space of A transpose is orthogonal to the column space of A. You'll recall this is one of the orthogonality relationships. So what we can do is we can write, actually I want to do this slightly differently. I'm going to change this and I'm going to make this Rn. And so this is the row space of A transpose plus direct sum of the column space of A transpose plus the null space of A. And here I'm using the fact that the null space of A is orthogonal to the column space of A transpose, and together they direct sum to Rn. So if X is in Rn, we can write X is equal to S plus R, where S is in the column space of A transpose, and R is in the null space of A. So this is very helpful to us. Here's why. And by the way, I should say this is unique, this expression. It's unique because this is a direct sum decomposition. So we can look at AX, and this is the same thing as AS plus R, which is the same thing as AS plus AR, which is going to just be equal to AS, since R is in the null space of A. So, since S is an element of the column space, give me a second, this froze. This is not going to recover. All right, so that was a thing that just happened, but I'm going to continue onwards. So where was I? I was talking about the theory behind least squares. And so in particular, I was using the fact that Rn was equal to the null space of A, direct sum, the column space of A transpose. And I was saying that if I had an arbitrary vector x in Rn, and by the way, A is an M by N matrix, then I can write x as equal to S plus R, where S is in the column space of A transpose, and R is in the null space of A. So AX is equal to AS plus AR, which is actually just equal to AS because we have AR is equal to 0, knowing that R is in the column space. And so S is equal to S is equal to A transpose Y for some Y. Now that we have this, this is the same thing as A transpose Y. And let's go back to our original equation. We were interested in solving the equation AX equals B. And B here is an element of Rm. So in particular, we can use the fact that Rm is equal to the direct sum of the null space of A transpose, direct sum the column space of A, to write B is equal to we'll say M plus N, and here M lives in the column space of A, and here N lives in the null space of A transpose. So we get AX is equal to M plus N, and N is orthogonal to R of A, simply because this is orthogonal to this. So the best we can hope for is making A of X here equal to M. And if we multiply both sides of this equation by A transpose, we get A transpose AX is equal to AM plus AN. But since we know that this should be transpose. Since we know that N is an element of A transpose, we know that A transpose times N is 0. So we just get A transpose M plus 0, and we get A transpose A times X is equal to this. So in this case, all we can do is we can multiply both sides by the inverse of A transpose times A to find A transpose A inverse times A transpose M. And we're using the fact that A transpose A is non-singular when A has linearly independent columns. Okay. So this is basically the main theory behind least squares. I guess I should show you guys one other thing. So let's look at this. AX is equal to M plus N. Then AX minus M is an element of the column space of A transpose. Wait, hold on. No, I'm sorry, is an element of the column space of A. So the magnitude of AX minus M minus N is going to be equal to the magnitude of AX minus M plus the magnitude of N by the Pythagorean theorem. And the fact that N is orthogonal to the column space of A. So this shows that this is always greater than or equal to the magnitude of N. So the best we can hope for is to make this quantity exactly equal to the magnitude of N. And that's what the least square solution accomplishes. And that's what the rest of this proof does. So that's the main theory. I covered it a bit better in lecture, so you can go back and watch that again. And if you want, you can also read the calculus approach to this problem. I don't want to show that right now. It's kind of a bit too tedious. So let's go back and see what other questions people have. Marcus asks, just to cover all the bases here, are there any other applications we should know of least squares for besides distance, approximating lines, and approximating quadratic functions? Okay, so let's see. Kyle asks the tank problem. What are you referring to here? Let me go get some water. You guys can ask more questions while I'm gone. I'll look when I get back. Do you guys want to see me do a statistics problem? Or would you rather see something else? I can try to. The thing about the exam 1 solutions is, in comparison with exam 2, you can basically compute all of them by using a calculator. So for example, I can at least sketch the main ideas of solving them real quick. Let's take this and get rid of this too. I'm not going to bother with 7 because that's just a matrix multiplication problem. But I'll look at the first few and talk about how to solve them. So this is exam 1. Let me go over what's involved in them. So for part A, what you do is you write down the augmented system 1, 1, 3, 10, 11, 2, 4, 6, 5, and you put your little augment bar, 1, 3, -1, and to solve for x, row reduce until the left side is in, or in this case I3. And then after you do that, the thing over here will be x. The right side will be x. This one I'll actually just solve real quick. 1, 2, 3, 4, 6, 6. Again, I put my augment bar. I have 1, 5. So first thing I do is I set row 2 to be equal to row 2 minus 4 times row 1, in which case I get 1, 2, 3, augment 1, and then 0, -2, and then -6, I believe, and then 1. So let me study this for half a second. Yeah, this looks right. The next thing I do is I set row 1 to be equal to row 1 plus row 2. If I do that, I get 1, 0, -3, augment 2, and then 0, -2, -6, 1. And then finally I set row 2 to be equal to -1/2 row 2. If I do that, I get 1, 0, -3. This stays 2. This becomes -1/2. And then I have 0, 1, and 3. So this tells me that this right here and this right here are bound variables. This right here is free. So I find that x1 is going to be equal to 2 plus 3 x3, and then I find x2 is going to be equal to -1/2 minus 3x3, and this solves 1b. Now let's look at part 2. Right here, the answer to this is just going to be the determinant, or rather the absolute value of the determinant. 1, 5, -1, 2, 3, 5, 1, 2, 6. And you can compute that determinant however you want. This is simply a cofactor expansion, and I'm not going to do this. I did this part earlier today already. For this one, we want to find all x values such that this is singular. As you may by now understand, what I'm actually doing is I'm looking at the characteristic polynomial of A. So PA of x here is going to be 1 minus x times 7 minus x minus 6. And so this is the same thing as x squared minus 8x, and then plus 1. And so the solutions are the roots of x squared minus 8x plus 1. So that's how you solve problem 4. And then part 6, or problem 6, this is where you compute A inverse. Actually, let me do problem 5 real quick. So I'll do 5 up here. What I know is that I know A4 is equal to 0, and I want to show that I minus, I'm setting B equal to I minus A, and the problem is show that B is non-singular. So how do you do this? Well, we're just going to multiply I minus A with I plus A squared plus A cubed. And if we do this, what we get is we get I plus a squared plus a cubed, and then minus a squared minus a cubed minus a to the fourth. Well, this cancels with this cancels with this cancels with this, and this right here is just equal to 0 by assumption. So this gives me I. So I plus a squared plus a cubed is the inverse of I minus a. So that's straightforward enough, and this shows that because I minus a has an inverse, it is non-singular. And then finally, I will do the last part of this problem, or the last problem, A inverse. So there is the smart way and the dumb way to do this. Actually, I don't think either of them. The only reason one way is smart and one is dumb is that one requires more computations. So the fastest way to do this to compute A inverse is to use the adjugate matrix. All right, so in order to do this, we have to compute a bunch of determinants. The first thing we're going to do is we're going to find the determinant of A. The determinant of A is equal to 1 times -1 times 2 plus 5 times 1. Let me not be sloppy. It's -5 times 1. And then minus 4 times -1 times 11, or -11, minus 1 times 1, and then plus 3, -1 times 2, minus 1 times -5. So here I just did a cofactor expansion along the first column. So let's solve this. This is the same thing as 1 times 3. So 3, and then minus something. So the first thing here is 3. The second thing is 11 minus 1, so minus 40. And then 3 times something here. What is this something? So -2 plus 5 plus 3. So plus 3 times 3, so plus 9. So this whole thing ends up being equal to -28. Did I do this right? I think so. So then here, this is -28, and what else do we have to do? Then we have to write down the adjugate matrix. So recall that Mij is equal to the matrix with the ith column, and, ith row, and jth column removed. And so what we're going to do is we're going to set Aij to be equal to the determinant of Mij times -1 to the I plus j. And if we compute all of these entries for differing I and j, we'll get the adjugate matrix. So A11 here, we omit first row, first column, and here we're just going to have a +1. So +1 times 55 minus 2 is equal to 53. And then A12, this time I'm going to have a -1 on the outside. So again, I omit the first row and the second column. So I'm going to get -44 and then -6. So this is actually going to be equal to +50. And then I'm going to get A13. This is going to be equal to, let's see, +1 over here, and then first row, omit the third column. So 4 times 1 minus -5 times 3, it's just 19. And then I'm going to compute A21, A23, A22, and then A23. So A21, I omit the second row and the first column, and I get a -1 for a sign, and then I get 11 minus 1, so 10, and this is equal to -10. For A22, I omit the second row and the second column, and I'm going to have a +1 outside. So 1 times -11 minus 1 times 3. So this just ends up being equal to -14. And then I'm going to have a -1 on the outside. And then this corresponds to omitting the second row and the third column, which is going to give me -1 times 4, because 1 times 1 minus -1 times 3. This gives me -4. And now finally I need to compute A31, A32, A33. So let me go through these really quickly. A31, I omit the third row and the first column. So I'm going to get +1 on the outside, and then -1 times 2 minus, well, actually just +5. So this ends up being equal to 3. And then here for A32, I omit the third row in the second column, and now I have a -1 out here. So third row, second column, so I'm going to get 2 minus 4, so when I combine all this, I'm going to get +2. And then finally for A33, I omit the third row and the third column, so I'm looking at the determinant of this. And I'm going to have 1 times -5, and then minus -1 times 4, which is going to simplify to simply -1. All right, now I have nearly all the information I need to assemble my inverse. Let me think about this for 1 minute. To make sure I'm okay with it. Let me look at this computation as well and sanity check myself. So determinant calculator. I just want to make sure I'm not being an idiot. 1, 4, 3, -1, -5, and 1, and 1, 2, -11. Let's make sure I didn't mess this up. I thought I messed it up. Okay, so somehow this should have been 22. So I'm not going to go through and do it again to figure out how exactly I messed it up, but yeah, I recalled that this determinant was 22. Yeah. I'm pretty confident with all of these though, so let's go about trying to assemble the answer. So, here is what you need to know. We have the following relationships. That the direct sum of Aij with AJK. This will be the sum from, hold on 1 second. So what do I know? I know that A1 times A11 plus A12 times A12 plus A13 times A13 is equal to the determinant of A. Okay, so the relation of interest to me is that the direct sum from J equals 1 to N of Aij and big A Kj, or actually sorry, yeah, Kj is equal to 1 if I is equal to K and 0 otherwise. So this is one of those relations I proved way back in lecture. I just had to remind myself what it was. And this is the relation that allows us to use all this data to write down the inverse. Because here's what we're going to note. We're going to note that what we need to do is we need to put this entry, and this entry in the first column of the inverse. So we're going to have A inverse is equal to 53, 50, 90. Or, sorry, 19. And then for the second column, we're going to use these entries, -10, -14, and -4. And then for the final entries, we're going to use 3, 2, and -1. And then we have to multiply all of this by 1/22. And so this is how we find the inverse using the adjugate matrix. And to sanity check myself, I'm going to try to see if we actually computed the right thing. So let's compare this with what Wolfram alpha would give us. So 1, 4, 3. Or this is not Wolfram alpha, but whatever. -1, -5, and 1. And then 1, 2, -11. So I get the right thing in the bottom two components as well as in this component. I get the right thing here. 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 And I get the right thing here. So our answer is correct. So that is how you can use the adjugate matrix to solve the inverse. The alternative method to finding the inverse would have been to write down the augmented matrix 1, -1, 1, 4, -5, 2, 3, 1, -11, and then you put an augment. And you put 1, 1, 1, 0, 0, 0, 0, 0. And then you try to do row reduction until the left side is I2. And if you do that, the right side will be A inverse. So the reason I didn't do row reduction is because it's, for the case of this specific matrix, the computation ends up being very, very ugly. And at least for this, I mean, it's just computing a bunch of 2x2 determinants and one 3x3 determinant. And if you do that, you can assemble them all together and you get the answer. Okay. Yep, the final exam is on August 4th, which is Friday at 1, oh no, Tuesday at 1 p.m. Okay, Hannah asks, can I explain diagonalization again? So let's do a diagonalization problem. What I'm going to do is I'm going to look at the matrix. How about 3, 2, 5, 1. So A is equal to this, and my problem diagonalize A. So let's go through this. First thing we do is we write down the characteristic polynomial of A. So this is the determinant of the matrix 3 minus lambda, 5, 1, 2 minus lambda. And this is going to be 3 minus lambda, 2 minus lambda, minus 5, which is going to become lambda squared minus 5 lambda, and then plus 1. And so the roots of PA lambda are going to be given by the quadratic formula, which is plus minus something divided by 2, and that something is negative 5 squared minus 4ac, so just minus 4. So this is equal to 5 plus minus the square root of 21 divided by 2. So what we can do is we can then try to find the eigenvectors associated with lambda 1 equals 5 plus the square root of 21 divided by 2. And this is the same thing as the null space of, let's see, 3 minus 5 plus square root of 21 divided by 2. 5, 1, 2 minus 5 plus the square root of 21 divided by 2. And then this is going to be the same thing as the null space of, give me a second to think about this. So I'm going to have 1/2. I believe it's 1/2, yes. Minus the square root of 21 divided by 2. And then 5. And then 1. And then down here I'm going to have, let's see, negative 1/2 minus the square root of 21 divided by 2. And so this right here is going to be equal, by our little trick, to be the span of 5 and then the square root of 21 over 2 minus 1/2. So I'm going to sanity check myself real quick to convince myself that this works. just do this over here. 5 minus -1, 1 half plus the square root of 21 over 3, and then -1/2 plus the square root of 21 over 3. So maybe something went wrong. I just want to think about why something may have went wrong. Give me a minute. Oh, okay. The mistake was what I typed in here. This should have been a 2. This should have been a 2. But this is still not correct. Okay. All right, never mind. What I did here was actually correct, so I have the correct vector. And thus, v1 equals 5 square root of 21 over 2 divided, or minus 1/2 is an eigenvector for A with eigenvalue (5) plus the square root of 21 over 2. So now I have to find an eigenvector associated with the other eigenvalue. So the eigenvectors associated with lambda 2 equals 5 minus the square root of 21 divided by 2. This is the same thing as looking at the null space of 3 minus 5 minus the square root of 21 divided by 2, and then 5 and 1, and then 2 minus this. Well, this is going to be the same thing as looking at the null space of the matrix. 1/2 plus the square root of 21 over 2. 5 1, and then negative 1/2 plus the square root of 21 over 2, which is just going to be equal to the span of the vectors -5 and 1/2 plus the square root of 21 over 2. So I'm not going to sanity check this because I'm very confident that it's correct. So thus V2 is equal to -5 in the first component and 1/2 plus the square root of 21 over 2 in the second component. So this is an eigenvector for A with eigenvalue (5 minus the square root of 21 divided by 2). All right, now set E to be the set of the two vectors. The first vector is 5, and then square root of 21 over 2 minus 1/2. And the second vector is -5, 1/2 plus the square root of 21 over 2. And we can write down the following diagram. So we have R2 with the standard basis. And we have a linear transformation given by the matrix. A is equal to 3, 5, 1, 2. And then we have our new basis E, which is made of the eigenvalues. So we can look at coordinate vectors with respect to E. And with respect to this basis E, we know how the matrix acts on E. If this is V1 and this is V2, then we know that A V1 is equal to lambda 1 V1, and A V2 is equal to lambda 2 V2. So this acts via the diagonal matrix D, where here I have lambda 1, lambda 2, and a 0, 0. So lambda 1 is 5 plus the square root of 21 over 2. And lambda 2 is 5 minus the square root of 21 over 2. And then we also have a map from this to this, and from this to this, given by a matrix S, where the first column of S is V1 and the second column of S is V2. And likewise over here, we have that the first column of S is V1, the second column of S is V2. So this shows that D is equal to A times S inverse on the left and times S on the right. And so this right here this is the diagonalization of A. So that completes the diagonalization problem. So in general, diagonalization basically works by taking a given matrix and finding the eigenvectors of that matrix. If it has n linearly independent eigenvectors, then with respect to the basis formed by those eigenvectors, the matrix will be diagonal, or the linear transformation will be given by a diagonal matrix. So you should think of diagonalization as basically a technique to take an arbitrary matrix and find a basis in such that it looks like this, which is to say the only non-zero entries are along the diagonal. All right, so that completes this problem. Let me look at the other question that was asked. So this was from Savannah. So I want to do the last problem on the optional homework. So I should go over here and pull this up. So for each of the following, find a matrix B such that B squared is equal to A. So let me illustrate how this is done. To solve this, what we do is we write A as the conjugate of a diagonal matrix, where D is diagonal. Say it looks like this: lambda 1, lambda 2, blah, 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 lambda n, and then zeros everywhere else. So, and then we set the square root of D to be equal to the matrix with entries square root of lambda 1, square root of lambda 2, blah, 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 square root of lambda n. So all I'm doing is I'm taking the square root of everything along the diagonal. Then, if you set B equal to S inverse times the square root of D times S, then B squared is going to be equal to S inverse times the square root of D times S inverse times the square root of D times S, which is going to be the same thing as S inverse. This S cancels with this inverse, so I just get the square root of D times the square root of D times S. Well, the square root of D times the square root of D is clearly seen to be just this matrix D, so this becomes S inverse times D times S, which is going to exactly be A. So the key point of this homework problem is to try to diagonalize your given matrices A, and then you take the square root of the diagonal matrix just by taking the square root of all the entries along the diagonal. Then you conjugate the diagonal matrix in the same way that you would conjugate it to obtain the original matrix, the original diagonal matrix to get A, And this will give you a square root. In fact, you could use the same strategy to find an nth root in general. So let's carry out this strategy. We're going to look at A is equal to 2, 1, and then -2, -1. So A minus I2 lambda is going to be the matrix. 2 minus lambda, -1 minus lambda, 1, -2. And the characteristic polynomial is going to be equal to the determinant of this. So 2 minus lambda times -1 minus lambda, and then plus 2. And now what do we do with this? Well, we get lambda squared, and then we get minus 1 lambda, and we get -2, we get plus 2, and so this just ends up being equal to lambda squared minus lambda, which is the same thing as lambda times lambda minus 1, and I do not trust this at all. I must have messed something up here. Oh, no, I didn't mess anything up. Okay. So we get this, and so the roots of PA lambda are 0 and 1. So I can easily check that the eigenvectors associated with lambda 1 equals 0 is going to be the span of the vector 1, -2. And I can also see that the eigenvectors associated with the eigenvalue lambda 2 is equal to 1 is given by the null space of 2 minus 1, 1, -2, and then -1 minus 1, which ends up being the same thing as the null space of the matrix 1, 1, -2, -2, which is the same as the span of the vectors 1, -1. Okay, so I have found the eigenvectors associated with the eigenvalues. So now let me write down my diagram. With respect to the standard basis, I have that A is given by the transformation 2, 1, -2, -1. And with respect to the new basis E, where E has vectors 1, -2, and -1, 1, it's given by a matrix D, where D is equal to 0 and 1. And I also have a change of basis matrices going up like this. And they're given in this case by S. Actually, I'm going to use a different letter this time. I'm going to use the letter T. So where T is equal to 1, -2, and -1, 1. And this is also T. So here's what I can do. I can note that the square root of D is actually equal to D. And the reason you can see this is that you take the square root of 0, you get 0, take the square root of 1, you get 1. So, since A is equal to D, T inverse on the right, and then T on the left, we actually have to have that this is equal to T square root of D, T inverse, which means we should have that A squared is equal to A. Let's check that that's true, and if it's true, then we're done. So let's see if I multiply this by this, first column by first row here, I get 2. If I multiply this by this, I get -2. If I multiply this by this, I get 1. If I multiply this by this, I get -1. So in fact, we have that A squared is equal to A. And the reason we were able to figure this out so easily is that the square root of D here was just this matrix 0, 0, 0, 1, and it's very easy to see that the square root of D is simply D. However, we could have done this a little bit differently. So let me show an alternative formulation to this. First, let's note that T here is equal to 1, -2, -1, 1. In which case the determinant of T is equal to -1. So T inverse is equal to -1 times the following matrix. 2, 1, 1, 1. Let me sanity check myself on this really quickly. Yeah, this is correct. So here's the fact I'm going to observe. If we set K to be the matrix 0, 0, 0, -1, then in fact we have K squared is equal to 0, 0, 1. So what we're going to do is we're going to compute K and then times T inverse on the left, and then times T on the right. So this is going to be the same thing as, let's go through it. 1, -2, -1, 1, and then times 0, 0, -1, and then times something. And the something is going to be T inverse, which I know to be this. So let's simplify this. I multiply this matrix by this matrix. I get 0 here. I get 0 here. I get 1 here. And I get -1 here. And then I multiply it through by this matrix. And let's see what I get. I get 2 here. I get negative 2 here. Actually, I get negative 2 here because of this negative sign. I get 2 here, and then I get 1 here. No, negative 1 here, and then I get positive 1 here. So I obtain this matrix B, but we can quickly see that B squared, which is going to be the same as negative 2, 2, negative 1, 1, is actually just going to be equal to this times this ends up giving me positive 2. This times this ends up giving me 1. This times this ends up giving me negative 2. This times this ends up giving me negative 1. So I get this matrix, which is just A. So observe that I have found 2 solutions to the equation B squared is equal to A. One is A itself, and the other is this matrix B, which is very similar to A, except the first row is negative and the second row is positive. Okay, so do I want to do the next one? This is what I'm wondering about right now. I'm not going to do the next one because it would take too much time and my brain is starting to get fried. But the general procedure is basically the same. For B, the eigenvalues are 9, 4, and 0, with eigenvectors. Let's see if I can figure these out in my head real quick. So the eigenvalue of 9 is really easy to see. It's 1, 0, 0 for 9, and then for 4, it's going to be 4 minus 9, 0. And then, 1 is an eigenvector, not 0. 9, 4, 1. And then for 1, let me think about that for a minute. Oh wait, I'm sorry. This should be negative 5. And then for 1, the eigenvectors will be, let's see, I can't do that calculation in my head. Okay, so basically what you have to do to find the matrix B for the case of the second part of the problem is you have to find the eigenvalues of the matrix first. In this case, 9, 4, 1. And you can then find the associated eigenvalues. In this case, it ends up being, this isn't right either. Now it's right. Wait, is it right? If I subtract 4 from this, I get 0. If I subtract 4 from this, I get 5. So yeah, that's the second eigenvalue. And let me just test something real quick, because I think I have some idea of what's going on. If I multiply this by this, and that doesn't work. But if I put a -1 here, and then I put a -1 here, does that work? Because then I would get -9 plus 5 plus 3, which would give me -1. Yeah, okay, so I am able to figure out that final eigenvector without doing any computation. And that final eigenvector is just -1, -1, +1. Sorry, you know what? I will actually finish this problem because it's not that bad. So let's take all this, let's go down here. What I do is I set my matrix T to be equal to the matrix 1, 0, 0, corresponding to the first eigenvector, and then 1, 1, 0, and then -1, -1, 1. And then the next thing you do is you have to compute a T inverse, which I'm not going to do. So I'll leave this to compute this yourself. And we have the following diagram. Our three standard bases, and our linear transformation is given by the matrix, this thing right here, 9, 0, 0, -5, 4, 0, and then 3, 3, 1. And now we have found the eigenvectors associated with the eigenvalues. So I'm going to put those down here. This is V1, this is V2, this is V3. V1, V2, V3. And right here, my diagonal matrix is given by something with 9 up here, 4 here, 1 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0 here. And I have T and T. So this shows me that A is equal to, well, I go down by T inverse, and then I go across by D, and then I go back up by T. And so in this case, what I can do is I can note that the square root of D is just equal to, well, one such square root is given by 3, 2, 1, 0, 0, 0. Maybe I'll even call this K. So what we can do is we can set B is equal to T, K, T inverse. And you can easily see that B squared is equal to A. And all you have to do is you have to compute T inverse, and then you have to do this matrix calculation. But if you do it, it will give you B. And B is going to be a square root of the matrix A. Sorry, I was being a little bit sloppy on this last one, but I'm kind of, my brain is starting to freeze. So T is the base change matrix from the basis E to the standard basis are exactly the eigenvectors. Okay, so that's how these kind of computations go. All right, so my mind is starting to fry, and I think I'm going to call it a night. Do you guys have any parting questions before I finish up? Okay, so given that, I'm going to end the live stream for tonight, and I hope you guys have... no. So, going to end for tonight, and I hope you guys have a good weekend, and I hope the final exam goes well for all of you. So I'll answer these last few questions. All right, so good night, everyone, and see you Tuesday.